In our last lesson, we were looking at probability trees like this with independent events. So the outcome of one event didn't affect what happened next. So here we have 5 red and 3 white counters in a bag. One's taken out and then it's replaced. Then a second one's taken out. So the probability it's red on the first pick is given here for us because 5 out of the total of 8 counters is red. Probability of white will be 3/8. Because it's replaced, these probabilities stay exactly the same on the second branches of our probability tree. 3/8 that it will be white, 5/8 that it will be red. To work out probability questions, so here we're looking that both taken are red. So the probability of them both being red, it was 5/8 times 5/8 gives us 25/64. Second question here is a little bit trickier. So we want only one of the counters to be red. There's 2 ways that can happen. It could be that the first one's white and the second one's red. Or it could be that the first one's red and the second one's white. We need to work out the probabilities for each of these and then add them together. So for it being white, then red. For it being red, then white. And you can see the probabilities for both of those are the same. As you're going through questions, just be aware when that does hold and also when it doesn't. So the probability for 1 red and 1 white, the order is unimportant. We need to add together those 2 fractions to find the probability there. Same question, apart from we're changing one thing. So this time, the counter is not replaced. The probabilities at the start will be the same. 5 in 8 chance it's going to be red. 3 in 8 chance it's going to be white. But whichever counter was picked first will affect what goes on next. Now we're looking here at dependent events. So what happens first does affect what happens next. So if we start off here looking with a white one taken first, there were 3 white counters left. Sorry, there were 3 white counters in there. So for the second one to be picked, there's now going to be 2 white counters in there. There were 8 in total, 1's gone, so there'll now be 7 in total. There were 5 red counters. If a white one was picked, there's still 5 red counters, but the total is 1 less than the original, so the total will be 7. If red was picked first, well, there's still the same amount of whites in there. There's still 3 whites out of the 7 which are left there. There's now 4 reds out of a total of 7 which are left there. And you can see on here that these are all out of 7 because we've had 1 of the 8 counters taken away, so that's going to be the same. But you can see the numerators for these fractions are different. The first event has affected it. So let's work out the same questions when the counter hasn't been replaced. So the probability, they're both red, is 5/8 times 4/7, which, not a surprise, is a different answer that we got when the counters were replaced. Calculating when only one of them is red, so again we could have the first one white, the second one red, or we could have the first one red, the second one white. And as before, to do the probability there, we need to add those 2 together. So 1 red, 1 white, the order is unimportant, which is why I'm writing it here differently than how I did here, showing red first, then white afterwards. Now, again, we can see this is a different answer than we had before, and it can be difficult to compare fractions sometimes with different denominators. This one is, in the first example, is the same as 0.47 to 2 decimal places. The one we've just calculated here is 0.54 to 2 decimal places. So you can see they definitely are different, but in answering a question, we would just leave it in the fraction form. Pause your video, have a try at this one. So we've got two sets of traffic lights. The probability a car is stopped by lights A is 0.4. And we know these two events here are going to add to 1 because it's exhaustive. Either a car will have to stop or not stop. So that's going to be 0.6. If a car is stopped by lights A, then the probability it's not stopped by light B is 0.7. So here it must be 0.3. If a car is not stopped by lights A, then the probability it's not stopped by lights B is 0.2. So it must be 0.8 up here. So we've completed this probability tree. So someone drove along the road and was stopped by just one set of traffic lights. Got to find out if it's more likely they're stopped by lights A or lights B. So we want to find which one of those two has the highest probability. So we need to find out the probability of stopped and then not stopped, the probability of not stopped and then stopped, and just see which one's higher. So here we have 0.4 times 0.7 and 0.6 times 0.8. So we can see here the probability of being stopped by lights B is higher, so we just need to make that nice and clear. Now pause the video here and have a try with the tasks in this sheet. There's only 3 questions in here and they're a fairly similar level, so you can just do the first one, check the answers. If you feel really confident, then move on to the next part of the video. But if you've done the first one, you're not too sure, use the next 2 as useful practice. Here we've got a similar kind of question, but because there are 3 possibilities, makes it a bit trickier. And there's also a couple of shortcuts we can learn that will help us with probability problems. So we've got 8 orange, 5 coffee, and 7 toffee chocolates left. So that's a total of 20. Take 2. And we want the probability that neither are orange. So for our first pick, it could be orange or coffee or toffee. And for our second pick, we have the same possibilities. And I'm putting them in the same order every time just to help me keep it organized. Now, if we're asked to complete the probability tree, I would need to put in the probabilities on every one of these. But takes quite a long time, and if we don't need to, we'll just put in the ones that we're going to need to use to find our answer. So for neither to be orange, it could be coffee then chocolate, or coffee then toffee, toffee then chocolate, toffee then toffee. So there's 4 possibilities we could have which won't include being orange. So let's put in the probabilities for these ones. So there are 5 coffee out of 20 originally. Now we could simplify this down to 1/4, but what we want at the end when we get these answers here is for them to have the same denominator because we want to add them up. So it's actually easier just to leave it in this form at the moment. So we had 5 out of 20, so 1 coffee's been taken. So the probability of the second coffee, one will be coffee as well, will be 4, 1 less, out of 19. There's still 7 toffees in there out of the 19. We started with 7 out of 20 toffees. The probability here will be 5 out of 19. Probability here will be 6 out of 19 because one of those toffees has already gone. So we need to multiply these pairs together to get the answers. And then we need to add them together. And that gives us the final answer of 132 out of 380. Pause the video, have a try with this one. First, we need to label the probability tree with the possible outcomes. And then we could fill in every probability on this probability tree, but we can just look for the ones we need to calculate this. So we need to find out the probability that biscuits are not the same type. Now there's 6 possible ways they could not be the same type. So we can just find each of these probabilities and then add them together. But there is a bit of a shortcut we could use here. Now, there's 3 ways that they could be the same type. And we know that all these 9 possible outcomes at the end, because they're exhaustive events, have all got to add up to 1. So we could do 1 take away the probability of getting 2 the same. And that will give us the answer as well. Just a bit of a quicker way to do that. So we'll work it this way and find these 3 probabilities. So there were 12 out of the original 20 were plain. For the second biscuit, it means there'll be 11 plain ones left out of the remaining 19. There were 5 out of 20 chocolate ones. If one's gone, there'll be 4 out of the 19 left. 3 ginger, so that leaves us 2 out of 19. So we'll work out the probabilities for each of these. And we now need to add these 3 probabilities together. So this is the probability of getting 2 the same. So we want to do 1 take away this value. And if it helps, we can think about the 1 here as being 380 over 380. So we calculate this. So the probability of them not being the same type is 222 over 380. There's just 5 questions in this second task, and the first one we just looked at in the your turn one you did about the biscuit. So if you've done that already, don't worry about doing it a second time. I would like you to try the other 4 though, as they are all slightly different problem-solving kind of questions. And this is the end of the main bit of the lesson. Make sure you check your answers. There are 2 extension questions, which I'll show on the video for a few seconds each. You can pause it for those, but they are also attached to the Show My Homework documents. Okay, good luck with these. Make sure you check your answers and please get in touch if there's something you're not sure about. This is the first of the extensions. It's a bit trickier than it may first look. I'll be really interested to hear how you get on with this. There are questions attached to Show My Homework. And the second one here, I know some people in my tutor group have seen this. So trying to find the probability that in a classroom of 30 people, at least 2 share the same birthday. Now, the 4 questions on the screen take you through the process for doing that, but the link down in the bottom right corner will take you to a brilliant video that explains exactly how this works, and I think you might be surprised by the answer.